Okay, so hi everybody. So today what we're going to do is start a new topic, and this is the idea of electromagnetic induction. And so everything we've talked about so far has been the static situation, either static electrostatics, where you have charges which are just sitting there and you want to know what the electric field is from those static charges, or the sort of steady currents that lead to magnetic fields. But we've never really allowed these things to have a dependence on time in the sense that they would be different from time to time to time. Even in the case of the steady electric current, that had a changing charge, but it was always changing kind of in the same way. It was always nice DC. It was always the same from time to time to time. And these gave us electric fields and magnetic fields and so on, which is very interesting. But it turns out that when we allow things to change in time, we get a much bigger variety of much more interesting things happening when you allow for time dependence. And so that's what I want to start talking about today. I want to talk about what happens when the situation, the fields in general, change with time. And this is going to lead to an idea that there's a very, very deep relationship between the electric and magnetic fields in a way that we'll talk about. And that's why we're studying electromagnetism as sort of one thing. Okay? So we'll see how that all comes about. In addition, it's going to lead to a number of very, very important devices for our life in general, things you've heard about and things you know about, plus some other interesting ideas. And ultimately, it's also going to lead to a very, very deep understanding of what electromagnetism really is, but that's going to take a little bit longer. Okay, and so we start today. We'll have a couple of lectures on induction. Okay, this is the first one. So far we've been discussing the equations, and the equations that we've got so far for our static situations, not solutions, but equations. Okay. The equations of electrostatics and magnetostatics. Okay. Electrostatics and magnetostatics. So in other words, situations in which the time derivatives of the fields is equal to zero. So dE dt is equal to dB dt, and that's equal to zero. Okay, so that's what I mean by the static situations. And so these things that we've seen so far, several equations. Okay, we've seen Gauss's law. Okay. Gauss's law both for the electric field, del dot E, is equal to rho over epsilon naught, or if you like, integral E dot dA is Q enclosed over epsilon naught. Okay, it's completely equivalent sort of way of writing these things. Gauss's law for magnetism, del dot B is equal to zero, no magnetic monopoles. B dot dA is equal to zero. We also saw that the curl of E, okay, this is a little bit different. So those were Gauss's law. Then we also have that the curl of E is equal to zero, which implies that E can be written as minus the gradient of the voltage, because you know that the curl of the gradient is zero. Okay. This also implies that integral, if I take E dot ds, integrated around a closed loop, this is going to be equal to zero. Because if it's a gradient, if you integrate a gradient along a line integral, then the value is just the voltage at the end points. And if you start and stop in the same spot, you're integrating over a complete loop, you get nothing. Okay? And then finally also we have Ampere's law, which says that the curl of B is equal to mu naught times J. That's a bad mu. Okay. Mu naught J. Okay. Which is equivalent to integral B dot ds is equal to mu naught times I through. Okay. And also, the fact that the divergence of B is zero means that we can write B as the curl of some other vector, the vector potential. And these are the things that we have seen so far. Okay? Every other equation that we've written down has been a consequence of these laws. And so again, just to remind you, which of these are true in general? Okay? This is true in general, and this is true in general, again, assuming that we don't have any kind of magnetic monopoles. And that means that this is also true in general. Okay? B is del cross A follows directly from here. And so if Gauss's law for magnetism is true, that means we have to be able to write B as the curl of some other vector. Okay? In addition, this law, Gauss's law for electricity, this is true. Okay? Which means also these integrals are true because they're exactly the same laws, just kind of disguised. Okay? Everything else here is only an approximation. Okay? It turns out that when we start allowing for time dependence, these equations here are going to change, which also implies that this one here is going to change. All right? And so these things we're going to have to look at. Okay? And in fact, this one here we're going to look at today. Okay? This one and this one. Okay? We'll save this thing for a little bit later. Okay? I can't tell you what this one is until we get to... actually, I take that back. No, we can talk about this one. But we're actually going to talk about these two forms, I think, next time, or maybe just right at the end today. Okay? But we'll investigate these two forms in more detail next time. Okay? But this one, I want to investigate today. Okay? And so, again, these are the static situations. Now we want to start allowing things to change with time. So we've talked about how you can produce magnetism with an electric current. If you have a wire, okay, if you got some wire and it's carrying a current, say in this direction, then you know that there's a magnetic field that circles around this thing, and the direction is given by the right-hand rule, so it comes out of the page up here and goes into the screen down there. And so a current produces a magnetic field. You might wonder if the opposite situation is true. Okay? You might wonder, well, suppose that I have a magnetic field. Can I use that to produce a current? Is nature kind of symmetric? And so it turns out that no, you can't if everything is sitting still. Okay? And you'll see the reason why. Suppose that you have a wire. Okay? Suppose you just a piece of wire, a piece of metal. You got a metal stick. Okay? So this is just a conductor, piece of metal. And suppose that you've got a magnetic field, and let's say it's pointing everywhere, say, into the page, okay, into the screen. So this is my B, and it's nice and uniform, it's constant and so on, okay? Actually, it doesn't matter if it's constant or not, it just makes everything easier. Set this thing here, okay? Now, if this is a metal, you know that there are electrons and protons and things like that all wandering around in there, okay? Electrons and protons, okay? The electrons are the ones that wander around, the protons sit still, okay? Now, if you set this stick here, if your velocity of your stick is equal to 0, then what does that mean? You look at the charges, okay? Look at some little charge Q inside this thing. You know that if this stick was moving, if the charges are moving, there's a magnetic force, which would be Q V cross B. Okay? If this stick is standing still, V equals 0, and that implies that the magnetic force is also equal to 0. So there's no force acting on these charges, and so they're not going to move. If there's no force which is making these charges move around, then they're just going to kind of sit there, or they're just actually going to keep drifting whichever way they're drifting. No force means no acceleration. It doesn't mean no velocity. Okay? And so a static charge in a static magnetic field, as you know, doesn't produce any forces. Now, then that gives an obvious question. What if we start it moving? Okay, what if we move it? Well, suppose you move this stick in the direction of the magnetic field, into or out of the page. If that's the case, there's still no magnetic force. Why? Because in that case, V cross B is 0. V cross B, as you remember, okay, the magnitude of it would be VB sine theta. And if V and B are in the same direction, theta is 0, or if they're in opposite directions, 180 degrees, but the sine of both of those things is 0. And so if you move this in the same direction as the magnetic field, then there is no magnetic force. Okay? So again, obviously now what we want to do is try moving this thing in other directions, say perpendicular. Okay? And that's what I got here. Suppose that again, I've got this magnetic field that points everywhere into the page in this picture. And now I take this thing here, and I move the stick in the direction, in this rightward direction. Okay, so this is my metal stick here. Okay, so this is my metal stick, and I'm moving it perpendicular to the direction of the magnetic field. And because of that, okay, if I consider a positive Q inside this stick, then maybe you can see from the right-hand rule, your very bad finger, V points, your thumb points to the left. The B, your index finger, points towards into the page, and then your middle finger, the F, the force, points up. And so there's going to be a net magnetic force on these positive charges up. Okay, that just comes from the right-hand rule. Or if you like, curl your fingers from V to B, and your thumb points in the direction. Okay, and so because there's a force on these charges, they're going to move. They're going to feel an acceleration. And the negative charges will get pushed downwards. Okay? And so there is a magnetic force acting on these things. Magnetic force, in this case, pushes positive Q's up, okay, or negative Q's down. But this means if there's a flow of charges, this is a current. And so by moving this stick around in the presence of a magnetic field, you've induced a current. Okay? So yeah. So yes, it is possible to use a magnetic field to produce a current, but you can't have a static thing. Okay? Something has to be moving. Now he said, I thought that magnetic forces don't do any work on these things. And that's true. They're not doing work on these charges. You are doing work because you're moving these things in the presence of this magnetic field, and that induces a magnetic force on these things. And then the charges respond to that magnetic force by moving up or down. Okay? And so, in other words, by creating a current. Okay? A current I. Okay? So, we do have a current. And now I want to try to understand something about this current. Okay? As I move this thing, what's going to happen? Okay, let me redraw it. Okay, as I move this, and again, this only lasts for as long as I am moving this thing. Once I stop moving it, then everything's going to kind of relax back down. Okay, because in particular, as I move this thing, more and more positive charges go up here. That's as far as they can go. They go up to the top here, and you put a whole bunch of positive charges up here, and then the negative charges get stuck down here. And so what have you done? Well, you've created basically a dipole. You've created an electric field in here. And so there is now an induced electric field. And I say induced because you have induced it. You have created this by moving this stick around inside this magnetic field. And this induced electric field, right, what's it going to be? Okay? Well, this induced electric field should be such that as you keep building this thing up bigger and bigger, you put more and more charge up top, you put more and more negative charge down below. So you create this electric field that points downwards. Okay? It goes from positive to negative. And so if you consider this same stick, and you look at some charge Q, it's got two forces acting on it now as you're moving this thing along. It's got the magnetic force, which points up, and then it's got the electric force, this new electric force, pointing down. Okay. Now, this is going to keep on going. Now, at first, the magnetic force is the biggest thing because you haven't put any charge up top or up bottom, so the electric field is very small to begin with, but as time goes on, you put more and more charge, you separate more and more charge through here, and then eventually, you build up a big enough electric field that these two forces here will be equal. And when that happens, this charge here isn't going to feel any net force. It either won't move or it's just going to keep moving in whatever direction it was going in, but the current essentially stops in that case. And so the current stops when the electric field gets as big as possible, when these two forces balance out, and that happens when the electric force equals the magnetic force. And you remember that the electric field force should be Q times E induced. Okay, this new induced electric field here should be equal to Q times V times B. And since V and B are perpendicular in this case, I'm just going to set the sign equal to 1. So the charge cancels off, and so I find that E induced is equal to V times B. So that's the size of the electric field that I build up. Okay? And so I've created a new electric field. Now, this isn't coming from some excess charge. Overall, this metal stick is electrically neutral. All I've done is to polarize it. All I've done is to push the positive charges one way and the negative charges the other way. So I create this electric field. But if I stop moving this thing, all those positives and negatives will repel each other. They'll attract the other ones. And so this stick will go back to being uniformly neutral. Okay? But as long as I'm moving the stick, as long as I'm applying a force to this thing, as long as I'm doing work on this stick in the correct direction, I've induced this electric field. That's kind of nice. Okay? I can also think about this thing in another way. Okay, let me redraw this. Okay? So here's my stick with my bunch of positive charges up here and my bunch of negative charges down here. And suppose that the length of this thing is L. Okay? Well, I know that there's an electric field across here which goes up and down. Okay, this is my induced electric field. I can think about this in terms of voltages instead. Okay? The electric voltage, okay, on this stick, which I can write delta VL, which I'm eventually going to write as E, okay, this same thing. As we've seen before for DC circuits, I'm going to write it this way, but for right now it's the delta voltage. You remember, hopefully, is minus integral E dot ds. Okay? Well, in this case, my E induced is nice and constant. Okay? Is, if you like, minus V, B, say J hat, if this is pointing up and down. And so in this case, okay, as long as I'm moving in a constant velocity, as long as my magnetic field is nice and constant, then the voltage should be nice and constant also. So I'm going to write my E induced. Okay, again, this is like a battery. Okay, so I'm kind of making a battery here. My E induced will be minus a minus VB, okay, minus from here and then also minus from here, integral, well, dy from 0 to L. Okay, why? Because ds in this case is just going to be dy j hat. I'm just moving up and down along the length of the wire. And so finally my E induced is going to be equal to VLB. Okay, and so this is my induced voltage. Okay, so I've created a voltage across this wire by making it, by moving it through a magnetic field. And the voltage that I induce depends on how long the wire is. So a longer wire will induce a bigger voltage. Moving it faster produces a bigger magnetic force on these charges, and so the current is bigger, and so the charge separation is bigger, and so then you end up with a bigger voltage. Same thing for the magnetic field. Okay? And so in this case, you just end up basically with sort of a battery. You've kind of created a battery by moving this charge through there. You've put a difference in voltage, and if you choose all your numbers so that VLB is, say, 9 volts, you made a little 9-volt battery. Okay? And so you can do all kinds of very interesting things. Instead of having this thing just move around, you could attach this to a wire. Or better yet, you could let this slide along a wire. Okay? Suppose that you just take this stick and just move it in this direction where you're sliding along a wire. Well, in this case, the positive charges move up, but when they get to this other wire, if it's a metal-on-metal contact, it's going to go around like this. So you induce a current. Okay? And so you can create a nice little circuit this way. Suppose you've got over here a resistor, say a light bulb, here, and you take this thing and you move this stick, okay? And these are just contacts here. Okay? This is just another wire. Okay? As we've seen, if you move this thing to the right, there's a current that goes up, and the current's going to go around in this direction. So there's going to be a current passing through this light bulb. And so there's going to be a resistance here. And there's going to be, from Ohm's law, well, better yet, from our DC circuits. Okay? Go around in a loop. Some of the changes in voltages through the loop is 0. Here, from this metal stick, you got this E induced. Then you drop the voltage, so E induced from your Kirchhoff's law, minus I times R is equal to 0. Okay? This is your Kirchhoff's loop rule. And the I times R from Ohm's law is your drop in voltage across this light bulb. And so this tells you that I is equal to the E induced over R. And so that's V L B over R. And so if you want the power in the light bulb, okay, which is your I squared R, hopefully you remember all this, then the power in that light bulb is V squared L squared B squared over R. Okay? So that's how many watts your light bulb would be burning. Okay, how much energy per second? Notice, the light bulb lights up if you move it to the right. Does it get darker if it moves to the left? No, of course not, because it depends on the square of the velocity. It doesn't depend on which direction you go. So either way you move this, if you move it to the right, the current flows counterclockwise. If you move this thing to the left, the current flows clockwise. Okay, so it flows in the opposite direction. All right, so see, nothing to it. Okay? And so what we found is that you have a situation in which you can create this sort of current flow in a circuit by doing sort of mechanical work, by moving some things around in the presence of a magnetic field. And again, the reason for that is that moving these metal pieces around in a magnetic field creates a magnetic force that makes the charges move around, okay? And that creates a current. So let me look at this thing here again for a second. This E was VLB. And if I redraw this thing here, like this, here's my stick. This side here has length L. It's moving in this direction with a velocity V. And suppose that the distance that this stick is from this edge here is X. And again, suppose that I got my B pointing everywhere into the page. Notice, if I move this thing outside the region of the magnetic field, then the current stops. As soon as I move this past the magnetic field, there's not going to be a magnetic force anymore, and so the current just sort of relaxes back. Okay? Now, you can see, I think, that V should be dx dt. The velocity is just how fast you're changing your position. Okay? And if L and B are constant, then VLB I can write as d dt of x times L times B. Okay? This is if L and B are constant. Okay? So I can write my E induced, okay, this induced voltage, as d dt of B times x times L. Okay, nice. But look at what x times L is. Okay? X times L is just this area here. Okay? It's the area. More specifically, it's the area through which B is passing. Okay? It's the area through which the magnetic field is passing. So in other words, this is the flux. Okay? So I can write that x times L is equal to A. And so my E is d dt of B times A. Right? And so that's another very interesting way of writing it. Okay? And so more specifically, you remember that B times A is equal to phi magnetic, this magnetic flux. That's interesting. Okay? We can actually generalize this to a more general situation. Okay? When B and A, so remember what this flux was. So here's your area here. Okay? Here's your area. Okay? It's got a certain size A. It's also got a little normal to this thing. Okay? It's also got this little dA here. Okay? Where this is your little n hat, your little normal to the area. And this thing here defines your area vector, which was A times n hat. Okay, you remember this from Gauss's law. We talked about that. Okay, if you have a magnetic field passing through here, so this is your B, at some angle theta here, then the magnetic flux would be B times A times cosine theta, you remember. Okay, why? Well, if B and A are perpendicular to each other, okay, so that if they're parallel to each other, if B is parallel to A, then phi magnetic is big, okay, as big as possible. It's maximized. Okay. When B is perpendicular to A, phi magnetic is equal to 0. In that case, the magnetic field, if this is your area, this is your n hat, and your B points in this direction, there's no magnetic flux in that case because the B is all passing around it. Again, this is Gauss's law. And so in general, you get this. And so for the constant B, then phi magnetic is B times A times cosine theta, but that's the same as B dot A. Okay. Moreover, I hope you remember that in the situation in which B was not constant, okay, then in order to figure out what that magnetic flux was, we had to integrate B dot dA over this surface, okay, over the area. In fact, let me write it that way, over the area. So this is a surface integral over the area. Okay, so that's nice. Now you say, wait a minute, I thought that this was equal to 0. I thought that's the whole no magnetic monopoles. No. The closed integral of B, the integral of B through any closed loop is 0. Through any closed surface is 0. This is through an open surface. Okay? This is not some closed Gaussian surface. So this thing is not equal to 0 in general. Okay? You see, that's what we got here. The magnetic field is passing through this surface here. Okay? And so there is some flux. I don't close this surface on itself. All right? And so you got to be a little bit careful about this. All right. So with this in mind, I can write my induced voltage, okay, all kinds of different ways. Okay? So my induced voltage, I can write it this way. So E is equal to d dt of phi magnetic. Because in the simple case, phi magnetic is just this. Okay, so this is d dt of phi magnetic in this simple case. But it also generalizes to the more complicated case in which you have to have an integral and so on. Okay? Remember, if B and A are, so in the different cases, just to remind you, if B is parallel to A, then phi magnetic is integral just B dA. Okay? The dot product goes away. If B is constant, so if B is perpendicular to A and if B is constant, then you get phi magnetic is just B times A. The B comes out, you integrate to get the area, okay? That area over which the magnetic field is passing. Okay? So I can write my induced voltage this way. It's the time derivative of this magnetic flux. If you like, it's phi m dot. As always, dots mean derivative with respect to time. Or you can write that E induced, okay, is d dt of integral B dot dA. Okay? All of this is fine. Okay? All of this is fine. It all means exactly the same thing. And so notice, what this says is a changing magnetic flux induces a voltage. Okay? And the key term here is changing because this thing is a derivative. And so if the flux is constant, then the derivative would be 0. And so you don't have any kind of induced voltage in that situation. Okay? But it's only when you have a changing flux that you end up getting an induced voltage. Now that has some interesting questions, but let's think about this for a little bit. Okay? How can you change the flux? Well, here's a couple of ways. So this is changing the flux, which, remember, the magnetic flux is integral B dot dA. Okay? Now there's a couple of ways. One, you change the area. That's what you're doing here in the first case. In the first case, you're moving the this coil of wire into the presence of a magnetic field. So the area here through which the magnetic field is passing is just that area. It's just this region where there's a magnetic field. Over here, phi m equals 0. There's no magnetic flux in this region here because there's no magnetic field, but there's a flux through there. And as you move this through, the area keeps getting bigger. So here you have, if you like, a dot is changing. Okay? This gives you the flux. This is what gives you phi m dot. But remember, there's a couple of other things. Okay? The magnetic field, the magnetic flux is basically BA cosine theta. Okay? Basically. And so one thing that you can do, besides changing the area, you can change the angle. So suppose that you take a coil of wire and you spin it in the presence of a magnetic field. Well, in that case, this theta here keeps changing. So the flux keeps changing as well. In particular, suppose you rotate this thing around at some constant rate. I guess I did it back. No, that's right. At some constant rate, say omega, where omega is a constant. In that case, your theta is just omega t. Okay? So, if your theta is omega t, then that means that your magnetic flux, if B and A are constant, so again, A is the size of this thing, this says that your magnetic flux would be BA cosine omega t. And so your magnetic flux dot, your E, would be equal to minus omega BA sine omega t. And so you'd have a situation in which the electric voltage is sloshing back and forth. Okay? It's alternating. Okay? Guess what you just made? You made a generator. Okay? You made a generator in this case. In the case of a generator, okay, which is a device for creating electrical current, electrical energy, you have a coil of wire. This is sort of the simplest case. You put a coil of wire in the presence of a magnetic field. And so there's this magnetic field that passes through here, and you spin this coil. Okay? And you spin this coil, and that produces this current, this voltage, which alternates. Okay? And again, what we found is that this E here was equal to some minus omega BA sine omega t. And that's basically what you've got plotted here. And so in this case, the electric voltage sloshes back and forth from some, we'll call this E0, okay, some amplitude of your voltage. This is how many volts you actually have. Your amplitude of your voltage sloshing back and forth times some frequency. And so what happens is that if you picture a wire and you picture those charges which are in that wire, okay, a positive charge here, for a while it gets pushed this way, then it gets pulled back this way, okay? And so it just oscillates back and forth. And so if you hook this up to some device, the charges get pushed into it for a while, then they get pulled out of it, then it gets pushed into it, and so on. And so this is your AC current. Okay? You're alternating current. Okay? And if you choose the omega to be 120 pi, so that in other words your frequency is 60 hertz, okay, because omega is 2 pi times the frequency, then you've got standard American AC current. Okay? I think in Europe it's 50 hertz and so on. Okay? And so there was a big debate way back in the early days between Tesla and Westinghouse and Edison and so on about DC current versus AC current and so on. And AC current eventually won out. Okay? The current wars. And that's because there's less losses. It's just a better sort of way of doing things. Okay? And so AC current. And so this is how you generate AC current. And so this is very, very nice. All right? We're going to talk about AC current when we talk about AC circuits later on, but this is a way of generating that. Okay? Now, here's something very interesting. Suppose instead of having this thing suppose you cut these wires here. Okay? Or better yet, suppose you replace this light bulb here with a battery. Okay? So replace this instead. Okay? So get rid of the light bulb and replace bulb with a battery. Okay? In that case, what happens? Well, in this case, you put some current through this loop. Now, you're putting a current through a loop in the presence of a magnetic field. What happens? Well, if you got a magnetic field, say pointing into the page here, and you've got a loop moving like this, okay, and a current heading, say, in this direction, velocity v here, then what do you get? You get a force on these charges. Okay? There's a force acting on these charges. And what does that force tend to do? It tends to spin the loop. Okay? And so it does the opposite situation. So if you take a loop and you spin it by hand or by some gasoline engine or something like that to rotate that loop in the presence of a magnetic field, you create an electric current. Now suppose you do the opposite. You run an electric current through a wire in the presence of a magnetic field. Okay? That's going to create a magnetic force on here, which is going to create a torque, which is going to want to spin this thing. And so now you can spin this loop of wire and use it to propel a car. You can use it to raise some buckets of water or whatever it is you want to do. In other words, you've created a motor. Okay? And so it's the same device. Generators and motors are the same device. They're just running backwards from one another. In one case, you are using a magnetic field to produce a current, okay? Which by rotating a wire in the presence of that magnetic field. In the other case, you're using a current in that magnetic field to rotate the wire. All right, so you see that this idea of this induced voltage is very interesting, very important, and it's essential for sort of life as we know it. Okay, you wouldn't have motors and generators if you didn't have this induction, okay, this induced voltage. Okay? All right, so let's see an interesting example here. Suppose you've got, let's say, so this is an example. Okay? There's something very, very interesting about this idea of magnetic flux that we'll come back to, but I want to do an example. Suppose you've got a ring, okay, a ring in a magnetic field. Okay. My thing, there it goes. Thing froze for a second. You got a ring in a magnetic field. Okay, just like this, a ring of radius r. But let's suppose that you are, say, cooling the ring. Okay? You know what happens when you cool something? It's going to tend to want to shrink. So the radius of this thing is changing with time. And just to make something up, suppose that the radius as a function of time is some r0, say e to the minus t over tau, where tau is just some number. Okay? And r0 is the initial radius of this thing at time t equals 0. Then I want to know, well, is there a current which is going to be induced in this ring as time goes on? Yes, there is. Why? There's going to be a changing magnetic flux. Suppose that this magnetic field here points out of the page, and you're taking this thing and you're shrinking this thing nice and uniformly so it shrinks radially in. Okay? Well, then the magnetic flux at any time should just be B times the area, and the ring and B are perpendicular to each other. I don't need a cosine. This should be that B times pi r squared. Pi times the radius squared. So pi r0 squared e to the minus 2t over tau. Right? And so that's going to be the magnetic flux as time goes on. Okay? It starts off as b times pi r squared, which is a constant, but then as time goes on, it decreases. Okay? And so the magnetic flux looks something like this. Okay? It dies away. All right, so if that's the case, is there an induced voltage? Yes, there is. And that's just phi m dot. Okay. My pen's having a little bit of a lag issue here. Phi m dot. So I just need to take the derivative of this thing with respect to time. And when I do that, I find that I get minus 2 over tau b pi r naught squared e to the minus 2t over tau. Okay, so that's my induced voltage. Okay. That's my induced voltage in that ring. Piece of cake, nothing to it. Okay, now let's ask, what's the direction of the current? Which way is it going to flow? Now there's two ways. It's going to flow along this wire. It's either going to go clockwise or counterclockwise. How do we figure it out? Well, you think about it. This ring is moving inwards. Okay, you picture some instant here. This ring is moving in that direction. So this is the direction of the velocity of the charges. Why? Because it's squashing. The charges are carried along with this thing. So in this case, if you think about the magnetic force on these charges, so there's some little Q there. You think about the magnetic force on these charges from the right-hand rule. If V points to the left and B points out of the page, then there's a force up. There's a magnetic force that points up here on this thing. And so that means that your current is going to go around in this direction. And so your current goes counterclockwise. Okay. What about over here? Well, you can check that in this case the magnetic force points in that direction, and so on. It's always going to be tangent to this. Okay? So nothing to it. Piece of cake. Okay. So very, very, very simple. Very, very easy ideas. Okay. Let's figure out another case. Okay. Suppose that you've got a solenoid. Okay. Incidentally, before I say that, suppose instead you were heating the ring. That would change this to a plus, for instance, and that would change the direction of your current. I think you can see. In that case, the ring would be moving outward, and so the magnetic force would be reversed because the velocity would be reversed, and it would be heading down. It would be heading clockwise. Okay, and so this would be a picture of your induced current. Notice the induced current gets smaller and smaller and smaller with time. Okay, so very interesting. All right, so again, also, well, if this thing has some resistance R, then the current in the circuit would just be your E over R. Okay, this would be an Ohm's law sort of thing. So you can write all this stuff down. And you can figure out if you hook this thing up to a light bulb, what would the power be? Well, it would be I squared R, and so on. Okay? And so it basically behaves exactly like your AC circuits, except it's just the E is not constant anymore. The E is some function of time. Okay? So let's do another example. Suppose you got a solenoid, and you remember these solenoids. Okay. In this case, you've got a this solenoid here, and I want to know, okay, and again, here's your solenoid up top. It's just this loop of wire. Down here, this is another picture here. This has just got an iron core, and you remember from our discussions of magnetic fields in materials, this means you've got this big magnetization inside here, where you get all those little magnetic dipoles pointing in the same direction, bumps up the magnetic field by thousands of times. Okay. So I want to figure out, well, what happens here? Is there going to be some sort of voltage induced in here? Okay? And so suppose that we've got a solenoid here, and I'll just remind you, the magnetic field, suppose that the solenoid has N total turns, okay? A length L, let's say, okay, with current I, okay, with some current I, which in general I'm going to let be I of t. And I'm not going to give the function right now. We'll maybe do a function a little bit later. But here it's just some general current which is changing with time. It could be AC current. It could be current hooked up from an RC circuit where the current is decaying as time goes on. Okay? It could be current hooked up to this thing. Okay? It doesn't make any difference. It's just I of t. Okay? Then I want to know, well, what's the magnetic field? I remember. We worked this out. I hope you remember that B of t, it's okay if you don't actually, is mu naught little n times I, where this little n is the number of loops per length. Okay, number of turns per length. Okay, do you wrap this thing up 50,000 times per meter or whatever? Okay. And now this thing here was constant, but because t changes, okay, because the current changes, then the magnetic field is going to change. So in this case, what's the magnetic flux? Well, we got to be a little bit careful. If I want to think about the magnetic flux, through which loop? There's a magnetic flux through each of these loops. And every time you go through each of these loops, you create a little voltage in each of the loops. Okay? And so basically you're stacking up one of these loops here on top of the next, on top of the next, on top of the next. And so the more loops you have, the more voltage you induce. And so this is a sneaky way of sort of cheating nature to get more energy. Okay? You want more energy from a given magnetic field, just loop more wires around. Okay? And so that's pretty cool. And so I can talk about the magnetic flux per loop, okay, per n. So in that case, the magnetic flux, suppose here's your loop. Suppose that the radius of this thing is a, and you got n of these loops, okay, over a length L. What's the magnetic flux per loop going to be? Well, that should just be phi m per loop should be the magnetic field, B of t, times the area of this thing, pi a squared. Okay? Then the total flux, okay? The total flux through the entire solenoid, phi m total, should be just the magnetic field flux per loop times the number of loops, times n. Okay? Every one of those things, every one of those loops contributes. And if you've got n of them, it bumps up a whole lot bigger. And so your phi m total should be B times pi. Well, let me write it a little bit better. N pi a squared times the b. But remember what the b was. B was equal to this mu naught. Let me write it this way. N over L times I. So when I take this thing and plug it in here, I find phi m, the total magnetic flux should be, let's see here, pi mu naught, pi a squared, n squared. Where'd the squared come from? Well, there's an n here. Then there's also an n in the definition of B. Pi a squared mu naught B over L times I as a function of time. So that's my magnetic flux. Okay? And this thing here does depend on time because the current depends on time. Again, sorry, there's a little lag on my pencil here for some reason. So this is my phi magnetic as a function of time. Okay? And again, it depends on time because the current does. And so what's my induced voltage? Okay? The induced voltage in this case, well, I just take the derivative of it. Phi m dot is my E induced, okay? My induced voltage, my induced EMF here. And this is going to be mu naught. Come on, pencil. Mu naught pi a squared times N squared over L times di dt. Okay? So it depends on how fast your current changes. This number here in front, this is a purely geometric thing about the solenoid. Okay? It depends on how many turns you have in this solenoid. The more turns you have, if you got twice as many turns, you get 4 times the voltage. That's very nice. Okay? If you got a bigger solenoid, that's a bigger flux, and so that means you got a bigger amount of magnetism, and you got a bigger amount of, you got a bigger amount of magnetic flux, and that means that you have a bigger induced voltage. Okay? A longer thing is a little harder to pass the current through there. It's a little harder to spread out that voltage, and so you get a smaller voltage. So this is a purely geometric property of the thing. And this is kind of like when we talked about the capacitor. If you remember the capacitor, okay, you had these two plates next to each other with a positive Q here and a negative Q here. And the capacitance was this epsilon naught A over D, where D is the distance between the plates and A is the area of the plates. This was how much charge do you store up. This quantity here depends on the properties of this solenoid, and it says how efficient is this solenoid at generating current. If this quantity is very big, it's a very easy way of generating voltage. If it's very small, it's very hard. It takes a lot of changing current to induce this voltage. And so this thing here, it's got its own little letter. This is called L, and L is what's called the inductance. Okay? The inductance of this thing. And so what you find is that the change in voltage through this solenoid, okay, delta V, okay, which I've been writing as my E, is equal to this L times di dt. Where again, for this coil, L was equal to mu naught pi a squared times n squared over L. Okay? But this is the important thing to keep in mind here. And again, in general, there's going to be a voltage drop. And so now we've got some new sort of voltage thing here, okay? Which is very interesting. Okay? This is a solenoid is an example of what's called an inductor. Okay? It's an example of an inductor. What's an inductor? An inductor is a very, very interesting device, which we're going to learn about the reasons for this when we talk about AC circuits. An inductor, okay, is like an inertia for current. What does that mean? If you've got DC current, then your current just passes through the inductor like a piece of wire. It doesn't do anything. But if your current starts changing, and you see that here, if your current starts changing, then if your current starts changing, then the inductor sets up this voltage, which is in the opposite direction. You get what's called a back EMF from your inductor. And that creates a situation in which it fights the change. The more your current is changing, the bigger your induced voltage is going to be. Okay, so the bigger this thing is here, the bigger that induced voltage is going to be, and it's going to be like a voltage drop. It's going to change. It's going to fight it. And so this inductor likes to keep the current steady. It likes to keep it as constant as possible. And this is just like the mass of an object, the inertia of an object. The inertia of an object resists changes in motion, resists changes in velocity. The inductor resists changes in current. And so if you want a situation in which your current in your circuit is kept steady, you want some inductors in there. Okay, again, we're going to talk about these a little bit later on. These are pictures of inductors, and they look like little solenoids and so on. Okay? And so these are examples of your solenoids. Incidentally, what's the units of solenoid, or sorry, units of inductance. Okay. Well, since delta V through your inductor is equal to, it's going to, well, just the magnitude of it, L times di dt, then L has got units is delta VL over di dt, which is volts per, well, amp per second, or volts seconds squared per coulomb, or something weird. This is just called H for henries. Okay, H. Okay, and so the units of inductance are in henries. Okay, which are these sort of horrible things, horrible units. We're going to talk much more about inductors and inductances later on. Okay, but now here's something, a very, very interesting question. Okay. Very interesting question, which is this. I figured out this thing here, okay, by saying I've got this changing current here, okay? I got a changing current which induces a changing magnetic field. And that magnetic field creates a changing magnetic flux. And of course, since the magnetic flux is changing, that means that there's going to be an induced voltage, okay? And after all, if I go back and think about this, well, if I know that phi m is equal to integral b dot dA, then phi m can change in at least 3 different ways, okay, or any combination of the two. Okay? To change phi m, okay, what can you do? 1, change A. That's what we did in this very first case. Okay, we changed the area through which the magnetic field was passing. Okay? Piece of cake. 2, change theta. Okay? That's what we did when we talked about the motors here. You change the angle of this thing, that induces a current. That changes your flux. But also there's 3. Okay, what's number 3? Change B. Okay. Change the magnetic field. If you change the magnetic field, then there's also going to be a changing magnetic flux. That's what we did here. Okay. In this case, the B was changing. Okay, coming back here, B is the function of time here. And so that gives the phi magnetic to be a function of time. Okay. Or if you want, change all 3 or any combination of them. Okay. But these are the 3 independent ways of changing the magnetic flux. Okay, so that's easy. Okay, that's nice. And so we can change things all kinds of different ways. Nothing to it. But here's an interesting question. Okay, suppose I've got this same, let's think back to this ring. Okay, so I've got this same ring here, and now I've got a magnetic field, say, pointing out of the board. Okay, and now let's keep a fixed radius here. Okay, so this radius here is just some r, and it's fixed, it's not changing. But now the B, the magnetic field, is some, well, this one seemed to work, e to the minus t over tau. So it's changing with time, but the size of the loop is not changing. Okay, so I want to work out, is there going to be is there going to be a current induced in this? Well, first of all, let's work out the magnetic flux. Phi magnetic, you know that's pi times r squared, the area, times b of t. And that should be pi r squared b0 e to the minus t over tau. Good. And so, yeah, since the magnetic flux is changing with time, then clearly there's got to be an induced voltage. And so that induced voltage should be just, again, phi m dot, which will be minus pi r squared over tau, b0 e to the minus t over tau. There you go. So yes, there is an induced current, an induced voltage, which means that there's going to be an induced current. Okay? Okay? Which would just be the voltage divided by the resistance. But here's the question. Which direction? Okay? Now you say, well, it's got to be counterclockwise or clockwise. Yes, but here's the thing. It's all well and good to say that this idea of changing magnetic fluxes tells us that there's got to be a current. But it's quite another question to ask, what force is pushing these things around? What force is making these charges move? You say, well, there's a magnetic force. But if there's no current to begin with, you picture some charge here. You've got the charges sitting still. Okay? V initial is equal to 0 for these charges. And because they're standing still, that means the magnetic force can never, ever get these things moving. Because after all, the magnetic force is V times B. And if your V is 0, it doesn't matter what your B is. It doesn't matter if the magnetic field is changing. These things are sitting still. Remember, magnetic forces do no work. Okay? And so then it becomes an experimental question. Do we see any current? The answer is yes, we do. And what is the direction of that? The direction will be this direction. How do I know that? Well, I'll tell you in a minute. Okay? So yes, there is a current. Okay? In this case, yes, there's a current, and it's in the counterclockwise direction. Okay? How do I get that? Again, I'll tell you. Okay? But the big question becomes, where the heck does this current come from? You say a changing magnetic flux. Yeah, but again, what force is making these things move around? It cannot be the magnetic force. Okay? It can't be. There's just no way of doing that. Because remember, force magnetic is Q times V cross B. If V is 0, then there's no magnetic force. And so there's nothing to get them moving. Right? And so again, the magnetic force, there is no magnetic force, so it cannot be magnetism which is making these electric charges move. And if that's the case, the only possible solution to this problem is that there's got to be some additional force here which is causing them to move. Okay. And what's the only other force that'll make charges move? Forgetting about gravity. Gravity's not going to make things go around in a circle like this. Okay. The only other force which can exist is there's got to be an electric force. Has to be. Okay? There's got to be an electric force which is acting on these charges. And moreover, it's an electric force that pushes them around in this direction. So there's got to be an electric field which is moving around this wire. And this newly induced electric field, which is circling around this wire, pushes those charges around. That's the only explanation that can make this thing work. And so, what do we find? Okay? A changing B has induced a circulating E. We've created an electric field, a circulating electric field. Notice there's no charges here. I mean, there's these charges, but there's no net charge. This is an electrically neutral wire. There are charges, but there are just as many positives as there are negatives. And so we've induced an electric field just like we induced an electric field up here. Okay? We induce this electric field up here by the motion of these things, by changing something around magnetism, around magnetic fields. We do the same thing here. But in this case, the changing magnetic field actually creates an electric field that circles around. And so this means that the curl of E is not 0 anymore. Okay? Del cross E is not equal to 0 because it's curling, it's circling around. And so we got to try to understand this thing, but this is something very, very deep. This is something very important, okay? Because this implies that magnetism and electricity are not two separate things. That by changing magnetism, you create electricity. And that's a very deep idea. Okay? This idea is called Faraday's law. Okay? And we'll write down the mathematics of it in a minute. But again, this is essential to understand that magnetism, changing magnetism, induces electric fields. You create electric fields without any charges around whatsoever. If you just take a magnet and wiggle it around, you're creating electric fields. Okay, that's what this is saying. And the more rapidly you wiggle that magnet, the more intense those electric fields will be. Okay, so this is deep. Now, how do we understand this thing? Okay, so, well, we know from our discussions that this electric voltage is equal to d dt of integral b dot dA. But I also know that my voltages can be understood as minus the integral of some electric field dot ds. Okay? Now, in this case, if I think about what that electric field is doing, it's going around here in a loop. So I need to integrate this thing over a closed loop because this induced voltage is making the current circulate around in here. And so all I have to do is just say, compare this to this. And then I get Faraday's law. In integral form. Which says integral E dot ds integrated over a closed loop. Okay, kind of like Ampere's law, is minus d dt of integral b dot dA integrated over an area bounded by that loop. Okay? And this law is incredibly important because this gives us motors, this gives us generators, this gives us wireless chargers, wireless things in general, radio frequencies, all of this kind of stuff. So much of modern electronics, so much of these sorts of ideas are essential to this, okay? On and on and on. Okay? And so there's some very, very deep ideas here, very important stuff which is contained in here, which we've only kind of scratched the surface on, okay? And suddenly you might wonder, is the reverse true? This says a changing magnetic field induces an electric field. Will a changing electric field induce a magnetic field? Okay, we got to wait on that one. Okay, I'll tell you more about that one later on. Okay, near the end of the semester. All right. So again, this is absolutely essential. Okay, and again, in words, what does this mean? Changing B induces creates E. Changing magnetism creates electric fields. Okay, so that's D. All right? And so we can understand that. So let's go back and think about this ring problem. Okay? Again, we'll do this example here. Ring. And then I'll tell you how do you figure out the direction. Okay, there's a little trick for remembering it. All right. Ring. So again, here's that same ring, same problem, same magnetic field, which I think I took to be out of the page. Okay. So here's my radius r. Here's my same magnetic field. B of t is B0 e to the minus t over tau. And my question is, what is E induced on the ring? Okay. What electric field is induced on the ring? Well, from Faraday's law, this should be integral E dot ds is equal to minus d dt integral B dot dA. Well, I did this side. I know what this side is. This is equal to minus d dt. This is my minus phi m dot. And I did that problem here. Okay, I got that right here. It's this thing. So I just multiply this thing by a minus sign. This should be pi r squared over tau times B0 e to the minus t over tau. I think that's right. Yeah. Now I just got to figure out the left-hand side. Well, you know that the electric field is going to circle around in here. Electric field. Okay? The electric field should circle around because it's making this current move around in this direction. So my electric field should point in this direction. And so the electric field is constant on the loop. And notice, I worked out this area here is the area of this same loop. So I take this loop to be some, constant radius r. If the electric field is constant along that loop, and if I walk in the same direction, then I've got that integral E dot ds should be equal to E integral ds, because E is constant, it's along the length of the loop. And we saw this from Ampere's law. This should be E times the length of the loop, 2 pi r. And so this should be equal to E induced times 2 pi r. And so the electric field induced on that loop will be r over 2 tau b0 e to the minus t over tau. Okay, and if you want some direction, you could put in a phi hat sort of thing. Okay, but that's the magnitude. See how it goes? Okay, and again, since the direction is positive, I know it's heading in that direction. Okay, since this is a positive electric field, I know it's going in the direction of increasing angle, and so it's going that way. All right? Now, so we've got this, okay? So we can figure this out. We can figure it out for all kinds of other situations here, okay? For instance, now, something I want to point out right away. I worked out the electric field on this loop, okay, on this wire. It's not at all essential that I work it out on the wire. I can ask, well, what's the electric field? Suppose I come over here, some distance r away from here. Is there still an electric field induced there? Yes, there is. If I had some charge, if I put a whole bunch of charges all around this wire, they would start moving as well. So there doesn't have to be a wire there for there to be an electric field getting induced in there. There can be an electric field anywhere in the region around here. So you can work out the electric field here as well. So in fact, let's see that. Okay, let's take another case here. Okay, so another example. Okay, solenoid this time. Okay, my inductor. And let's talk about it. And suppose that we take the case where the current is some function of time, I0 e to the minus alpha t. Okay, so I want to work out the same thing. I want to work out the electric field actually in two regions, inside and outside the solenoid, and see what I get in both cases. Okay, so what is E induced inside and outside the solenoid? Okay, so in other words, first thing I do is I come over here, okay, start here in the center, and come out here some distance r, and ask, well, what's the induced electric field out here? Then I come out here this distance r, and I ask, well, what's the electric field inside? Okay. How do I do it? Well, first thing I need to know is what's the magnetic flux? Okay. So the magnetic flux, well, remember the magnetic field, B is a function of T, will be the mu naught N I of T, which will be mu naught N, same N, remember N is your number of turns per length, times this I0 e to the minus alpha t. And alpha here is just some constant, just tells you how rapidly this current goes away. Okay? So I got that. Now the magnetic flux, well, let me write down Faraday's law very carefully. Integral E dot ds is equal to minus d dt of integral B dot dA. Okay? Now in this case, let's take these two cases, inside. Okay, so I look at the situation here. Here's the solenoid. And I say, all right, I'm going to come out here some distance from the center, r. Okay, and I'm going to take, I want the electric field at that point, and as I've got it drawn here, the magnetic field points into the page. Okay, so this is my B. So I know that there's going to be an induced electric field created at that position. It's going to circle around. Okay? And of course it has to circle around based on the symmetry of this thing. Okay? Again, these ideas of symmetry are very important. Okay, so along here, okay, E is constant, points in the same direction, so integral E dot ds should be E times 2 pi little r, where little r is the size, is the radius of this loop. Okay? And this should be equal to this side, okay? Minus d dt of b. Now, b is constant on here, and that's equal to mu naught, I write in green, okay, for the magnetic field, mu naught n I0 e to the minus alpha t times the area through which the magnetic field is passing, and that's this area here. You're only worried about how much flux goes through this area, because it's through the area of that same loop. So this will be times pi little r squared. Okay? And so when you take a derivative of this, you get mu naught n times alpha I0 e to the minus alpha t times pi r squared. And so solving for E inside means setting this equal to this, dividing by 2 pi r, you get E inside is equal to, the pi's cancel off, mu naught alpha n I0 over 2 r e to the minus alpha t. I think that's right. Okay. This is the induced electric field inside of this solenoid. All right. Nothing to it. Not so bad. Okay, I just follow the rules on Faraday's law. Okay, and that's it. Okay. Now, how about outside? Okay. Well, I do the same thing. Here's my. I try to keep the same colors. Here's my solenoid with my magnetic field, again pointing into the page. Notice outside, B equals 0 outside. It's a solenoid. We've talked about that. So now I want to come out here, some distance out here, R, and do the same problem. Well, again, I know that there's going to be this induced electric field because it is a time-dependent flux and so on. So I'm going to get my electric field out here, and I'm going to take a nice circle because of the symmetry. And so again, E is constant, okay, and so on and so forth. So my left-hand side, integral E dot ds, just becomes, again, E times 2 pi r, where this is the electric field outside. And this is supposed to be equal to minus d dt of my magnetic field, mu naught n I0 e to the minus alpha t times what? Well, now it's just times pi big R squared. Why? Well, the only region where there's a magnetic field is inside the solenoid. So the flux stops out here at the edge of the solenoid. Out here, okay, for the region from little r, from big R to little r, there's no magnetic field out here. All the magnetic field is inside there. So that's the only region where I include any flux. Okay? And so when I do that, this gives me the same mu naught alpha I n I0 e to the minus alpha t times pi r squared. Again, setting this equal to this, I get E outside is equal to mu naught alpha n I0 e to the minus alpha t times r squared all over r. Okay? Notice E inside at r and E outside at r are equal. When you plug in little r equals big R, you get the same thing. Whoops, times 2, if I put the 2 there. Okay, you get the same thing. And so if I was to make a plot of this thing, okay, the electric field versus distance, this induced electric field starts off inside. Okay, inside it grows with distance. So it grows until you get to r, and then it falls off as 1 over r. Okay, so this would be the induced electric field inside and outside of a solenoid. See how it goes? Nothing to it. Okay. Now, here's a very interesting question. Okay, we figured out the direction. Is there another way of thinking about how we can think about the direction in which the current flows without having to work out the electric field and things like that? Yeah, there's something called Lenz's law. Which is very interesting. Okay, and let me write it, and then I'll try to explain it. Okay. When you have a changing magnetic flux, you induce a current. Okay? Which direction does the current flow? Okay? Well, here's the idea. When you create a current through a wire, you create a new magnetic field. Okay? As soon as you got a current traveling through a wire, a loop of wire, you create a new magnetic field. Okay? Lenz's law says that the current, okay, induced in the loop, okay, the loop being, whatever loop you've got this changing magnetic flux through, moves in such a way that the new magnetic field, in other words, the new magnetic field you created from this new current, this induced current, okay, that the new magnetic field fights the change in flux. Okay? What does that mean? Okay, well, here's the pictures. Okay, you get the hang of this by examples. Okay, suppose you got a ring here, and you got a magnetic field which is growing in time. So here's your external magnetic field. Okay, and let's suppose that B dot is bigger than 0. So in other words, it's getting bigger. You get more and more flux. This implies that phi m dot gets bigger. And so you're going to induce a current. Okay, so this is, you're going to induce a current in this thing. Now the question is, which way does it go? Okay, if you look at it from the top view, the magnetic field is getting bigger. So this is your original magnetic field. So you're going to induce a current in here. And the bigger your magnetic flux change is, the bigger that current's going to be. Now, there's two ways in which this current can go. It can either go clockwise or counterclockwise. Okay? So this will be the current. Lenz's law says that the current's going to move in such a way that the new magnetic field that is created by this current, okay, so again, as soon as the current's moving through here, you're going to create a new magnetic field. Lenz's law says the new magnetic field created by that current fights this change here. In other words, since the flux is increasing, the current creates a new magnetic field that tries to drop that flux back down. So in other words, if red here represents my new magnetic field, it's going to point into the page. Okay? And so this is my new B, which comes from the current. And in order for that thing to happen, okay, you remember our right-hand rule for currents, the current has to move, in this case, clockwise. Okay, why? Because if you picture this loop here and the current is heading in this direction, the magnetic field circles around like this. Okay, goes out of the page, then when it goes into here, it points in. Okay, that's the idea. So again, the whole idea is we induce a current, and that current creates this new magnetic field, and that new magnetic field fights the change of this current. Okay, fights the change of that magnetic flux. So in other words, if the magnetic flux is increasing, Lenz's law says your new current creates a magnetic field that tries to drop that flux back down. Okay? And this can be because B is changing, or it can be your area is changing, or anything like that. Okay? Let's see another example. Again, you get the hang of this with examples. Suppose I take it in the opposite case. Suppose I take my ring here, and my magnetic field points, let's see a more complicated example. Suppose it's pointing down, but it's getting weaker. Okay? So suppose that I have this thing so that B dot is less than 0. Okay? It's getting weaker and weaker and weaker. Okay? Then in this case, if I look at it from a top view, in top view, for this case here, here's the top view. The magnetic field points into the page. Okay, so this is my original one. Now, because there is a changing magnetic flux, then in this case, Lenz's law says the magnetic flux is getting smaller. I want to bump it back up. I want to try to keep that flux steady. All right? This is like the inductor, by the way. I want to keep that magnetic flux steady. So my new magnetic field has got to point in the same direction. I want to try to bump it back up, so I add some more magnetic field to this thing. So this is my new B. And so what direction does my current have to travel in order for that thing to happen? Well, it's got to go in this direction. Okay? So you can try all these different ideas. Okay? And so again, we got two different ways of thinking about how we can induce a current through a loop of wire. One way is through magnetic forces. That's what we discussed up here. Okay? Magnetic forces make these things move around. Notice also, Lenz's law works here too. In this case, if I move this thing, this wire in this direction, the magnetic flux is increasing. Okay? So for V to the right, this implies that phi m dot is increasing. I got more flux through there. So I want to try to drop that flux down. So I create a new B through here that's got to point up. Since the magnetic field was pointing into the page, it's got to point up. Okay, so this is my new B. And the way that I create that is by having a current moving in this direction. Okay, and so everything's consistent with each other. So I can think about it from that point of view, that the current moves around because there's magnetic forces acting on it. But when there's a changing magnetic field, it is not that there are magnetic forces. There's an induced electric field that pushes things around, and the direction of that thing is given by Lenz's law. Okay? So again, you spend a little time on these things, and you actually get the hang of it pretty quick. Okay? But it does take a little bit of sort of careful thinking for a bit. All right. So this introduces Faraday's law. Again, very important. Let me write it down again. Integral E dot ds is equal to minus d dt of integral B dot dA. Okay? Now, the obvious question, is this always true? Okay? The answer, yep. So I'm going to put this sparkly box around it so you remember it. Yes. Okay? Yes, it's absolutely always true. Okay? Provided there's no magnetic monopoles. If there's magnetic monopoles, you'd add another piece to it, but we're not worried about that right now. Yes, this is absolutely always true. This is one of the 4 Maxwell equations. Okay? This is the integral form of Faraday's law. There is a differential form that we can write, okay, by remembering Stokes' law. And I just want to write it this time. Next time we'll discuss it in more detail. Okay, we'll remind ourselves of some of these properties and ideas and so on. And so I just want to write it down. Remember Stokes' law, or Stokes' theorem. It says that the integral of E dot ds can be written as integral of del cross E dot dA. Okay? The integral of the circulation of the electric field is the same as the integral of the curl, the surface area, integral of the curl of E. Well, if that's the case, and if this is equal to minus d dt of integral B dot dA, then I can relate these two things since it's over the same area. Remember, this is the area of some loop. This is the area bound by the loop. Okay, so it's the same loop. So if you integrate around a circle, this is your loop, and then the area here of that circle is that area. Okay, so let me rewrite it. So integral del cross E dot ds is equal to, let me take this derivative inside, minus dB dt dot dA, and I need a partial derivative now because when I integrate over the area, I get rid of the time. I get rid of the space. I integrate over position. The whole thing just depends on time. But when I take this thing in here, you know, B depends on space and it depends on time. And so setting these two things equal to each other, oops, sorry, this is not ds, this is dA. These integrals are equal to each other no matter what area we take, no matter what loop we take, and so therefore we get the differential form of Faraday's law, which says that the curl of E is equal to minus dB dt. Okay, and again, I'll put that same sparkly, well, I'll sparkle it in some other colors. Okay, because this is also always true. Okay, and now you see, if I go way back here, I've got the next of my Maxwell's equations. Okay, I got the next of these Maxwell equations. And so we've got a lot of pieces of this so far. We've got Gauss's law for electricity, Gauss's law for magnetism. Now we got Faraday's law. We got the magnetic force. We got B in terms of A. What are we missing? We're missing two pieces here. We've got the first part of E, and we got the first part of this last equation, but there's something missing here, and then there's also something missing here. In fact, I can even get this one here, but we'll talk about it next time, but just sort of for completeness, okay? Starting off with, okay, again, more details on this next time. I just want to sort of write it so that we can get it. Since del cross E is minus dB dt, and you know that B is del cross A, this is the same as minus d dt of del cross A, which is the same thing as which is the same as minus del cross dA dt. Whether you take a derivative of space first or time first, doesn't make any difference, they commute. And so del cross E is the same as minus dA dt. This is the same as del cross E plus dA dt is equal to 0. Well, this tells me that the curl of this quantity is always equal to 0, no matter what E and A are. That means I can write this quantity as minus the gradient of some potential, the voltage. And so E plus dA dt is minus gradient of V, and so E is minus gradient V minus dA dt. And since this is always true, and this is always true, this is also always true. So you see, we're starting to get into more deep things. So the electric field depends on the scalar potential, the voltage, and it also depends on the vector potential. Okay? And so, deeper things. And so now I got this. Here, maybe. So I've also got this. So there's one little piece missing, which is still going to have to wait a little while. But we are getting closer to having the complete laws of electricity and magnetism. And allowing things to change with time has given us a very rich set of new phenomena. Motors, generators, inductors, wireless charging, so many other things. Okay? So much of what makes modern living, modern technology great is Faraday's law. And so there's a whole bunch of very, very good, very deep things about this. Okay? So I encourage you actually to spend a little time looking at the Feynman lectures on these topics because there's some very, very good discussions in there. Okay? Next time, I want to talk a little bit more about this differential form of Faraday's law, talk a little bit more about these electric fields and so on. Okay, and just get a little more practice with this. Right? After next time's lecture, after that we will go on to talk about circuits, AC circuits. It'll get a little bit more sort of, again, down to earth in the same way that DC circuits work. And in fact, we've already done all the hard work for DC circuits or AC circuits. And so now it's just a little bit of math. And incidentally, we will be talking about some fancier math. We'll be talking about complex numbers also. Okay? So that's coming up. Right? So, but that's it for today. See you next time.